Mic test, check, hello. Okay, so we are going to have a complete rundown on the entire coverage for aromatic compounds. So this is in preparation for an exam that I'll take tomorrow. As of the time I'm recording this, I do have an exam tomorrow on this topic. So not just on aromatic compounds themselves. A big part of this video is going to be about EAS, which stands for electrophilic aromatic substitution. So there are 5 EAS reactions that we will look into. Reactions within the benzene ring itself and reactions that are found in reactions involving the benzene substituents. So I'll just list them down by word. So we have 4 reactions involving the benzene substituents. We have bromination, oxidation. Actually, no. Let's formally talk about that later. For now, let's start at the very beginning. So the benzene is the simplest aromatic hydrocarbon. There are some basic compounds that you have to remember. Give me a minute. Okay, so when we name substituted benzenes, we're gonna assume that for now the scenarios are such that the benzene ring itself is the parent chain. So let's say we attach an ethyl group, CH2CH3. This is called an ethyl benzene. Later on, we'll be having examples where we try to name a compound such that the benzene ring is a substituent, not a parent chain. So for now, it is a parent chain. Let's have another example. What if we added tert-butyl? So this is going to be called tert-butyl benzene. Okay, another example. So this is, we attached a chlorine atom. This is going to be a chlorobenzene. Okay. Okay, that's it. By the way, for the structure of benzene itself, this is called the Kekule structure. Other renders of the benzene is this, the one with the circle. But what is advised to be drawn is this one, the Kekule structure. Okay, so these are things that you have to memorize. So we have, so if you have a benzene and CH3 is attached to it, this is called toluene. Or in other words, methylbenzene. Yeah, methyl. This is an alkyl halide. In other words, a hydrocarbon that is attached to a parent chain. The parent chain being a benzene ring. So this is methylbenzene. But we call it toluene. Another, by the way, this is just the same as this. If we connect OH, this is now a phenol. In other words, OH is hydroxy group, no? So hydroxybenzene. Thirdly, we have what if we attach NH2? This is called aniline. This is going to be critical for what we have to remember later. NH2 is amino group, so aminobenzene. On the other hand, something related to that, let me just, mute that for now. Aniline, what's related to aniline is this. So instead of an amino group, we attach a nitro group, NO2. This is called nitrobenzene. Okay. So later, in one of the EAS reactions, actually the second one in my list, it's called nitration. We basically, towards the end of the reaction, this is our product. And by a certain process, we can convert it into aniline. This is the useful product. This is what makes nitration useful. I just can't remember what you call, I can't remember the reaction to make nitrobenzene aniline. Let me just recall. It's on the tip of my tongue. I think it has something to do with reduction. Yes. So you perform reduction in nitrobenzene. The catalyst, basically, in the arrow, we'll be formally discussing this later, but just to let you know. So we have H2 and palladium with carbon. So this is one of them, no? Palladium catalyzed hydrogenation. More specifically, the reduction process involved here is called hydrogenation. The process could also be iron catalyzed or tin catalyzed, using both of them using HCl or hydrochloric acid. Anyways, that's already too much for an introduction. We'll properly talk about that later. We will properly talk about that later. So, we have benzene sulfonic acid, SO3, rather H, not N. And then we have benzoic acid, might be familiar to you already. So C, we have O at the top, and then we have OH. That is benzoic acid. And something related to it, this is what makes it easy to memorize. This one is acetophenone. Acetophenone and benzoic acid have a similar structure. So for benzoic acid, the substituent here is OH. For acetophenone, the substituent is CH3. Later on, in one of the reactions involving the benzene substituent, we are actually gonna turn certain compounds into benzoic acid, regardless of what they look like, no? The condition is for as long as the benzene contains, rather an arene, contains at least one benzylic CH bond. So when we say benzylic, it's as in attached to a benzene. For example, toluene. The figure earlier, this one. So toluene has an alkyl halide, no? As its substituent. So when we apply KMNO4 or potassium permanganate, regardless of what your compound is, whether it's CH3 as a substituent or let's say isopropyl, for as long as the substituent has a CH bond, a benzylic CH bond, then the result is always going to be benzoic acid. So what do you call that reaction specifically? It's the oxidation of alkyl benzenes. So alkyl as in benzene having an alkyl group attached to it. One example is simply methane. Methane being attached to benzene. That is, I think, the simplest example of an alkyl benzene. Okay? So, okay, we're done with, again, benzene sulfonic acid, SO3H. That is going to be important later. I think that is the product of another EAS reaction, sulfonation. Let me just confirm if my memory is correct. Yeah, this is the product of sulfonation. This one, again, is the product of nitration. We can perform reduction, more specifically hydrogenation, using any of these catalysts to, sorry, the arrow is supposed to be the other way around. This one. From nitrobenzene to aniline. No? Any of these catalysts we can use. Okay? Alright. What else? We have xylene, just an extra. Although I think it helps if you memorize this too. What if, starting from toluene, we have another substituent that also happens to be a methyl group. So this is basically called a xylene. And the position of the second substituent actually matters when we name. So there are three things you have to know. Let's say this is your basis. If your other substituent is attached here, basically, let's say this is 1. So if it attaches either in this side or this side, that means CH3 is ortho to this substituent, no? So in this case, what we have right now, this is called orthoxylene, or simply O-xylene. What if the compound is attached here? There's another name for that. Although we still retain the word xylene, this is going to be called metaxylene. Coming from the position of our original substituent, our second substituent is meta to where it is, no? To where our original substituent is. So basically, 1, 2, 3, if it's at a third position, no? From where the original substituent is located at. So whether it's here or here, it's called metaxylene or simply M-xylene. So, following the same pattern, what if your figure shows that your second substituent is at the fourth position with respect to where your original substituent is. So this is paraxylene, or simply p-xylene. Okay? So take note. Okay. So yeah, I just mentioned to you the three ways that two groups can be attached to a benzene ring. Regardless of the positions, their attachment is different, no? That's already a given. They are still all considered isomers. In other words, they have the same molecular formula. So, okay, let's have an example. We are still in the lesson on naming, no? So, if the two groups on the benzene are different, so let's say the substituents aren't CH3, one of them is not CH3, we follow a certain rule. This is to alphabetize the names of the substituents preceding the word benzene. So we're still gonna assume that in this case, the parent chain is the ring itself, no? So let's say this is bromine, this is chlorine. So when we name this, they are ortho to each other, no? 1, 2. So ortho, and then by alphabet, bromine comes first. O, bromo, chloro, benzene. What if we have this? We have a nitro group, we have fluorine. So, okay. They are meta to each other, no? So M, nitro, and I think F comes first. So M fluoro, nitro, benzene. Okay. How about this one? Applying what I instructed earlier. So if you memorize the common aromatic compounds, then you shouldn't have a problem here. So what if you have this? So you can call this methyl benzene, but it's supposed to be toluene, no? By rule, or at least it's highly recommended. So one way to name this is, since the substituents are para to each other, we put P, and then, okay, bromo, and then, yeah, bromotoluene. Because this part is toluene. So we're just going to assume that we only have one substituent. What if we have this? NO2 and then OH. So they are, the substituents are ortho to each other, no? Only one position away. So O, what's this? Hydroxy group. But we're gonna call this phenol. So O, nitro, phenol. Nitro, because the substituent here is a nitro group. Okay? So, at least what I'm studying right now, the priority does not matter. What if you're given OH and CH3? So that's not part of what I have to know. So I'll leave that to you. If your professor requires you to study even the priority, I think that's reserved for chemistry majors. For Chem Eng majors, they don't have to know that. Okay. Practice. This is easy. Again, this is another render, another way to present the benzene ring. But for later, when we proceed to the mechanisms, the reactions, I think we have to, I think it's better, no, at least, to present our benzene ring in the way, in the cocculiform. Let's just call it a cocculiform. Basically the one with the lines. So this one, the substituents are para to each other. That's it. You just identify if it's meta, para, or ortho. We have NO2, NO2, or like O2N. So they are 1, 2, 3 meta to each other. Both nitro groups. What if we have this? So simple. This is ortho. Okay. So what if, okay, we are now in the part where we are going to name certain compounds such that the benzene ring is a substituent. Uh, so what are the rules? Sorry. We'll reserve that for later. There is something else that you have to know before that. What if we have 3 or more substituents on a benzene ring, not just 2? So there are rules, no? If we have 3 or more substituents on the benzene ring. So there are rules. You want to number to give the lowest possible numbers around the ring. And again, like what's been mentioned earlier, you have to alphabetize the substituent names by alphabet. And when substituents are part of common roots, for example, toluene, you know that it's this one, no? So you make use of that. You call this toluene, not methylbenzene. You name the molecule as a derivative of that monosubstituted benzene. Okay, let's have an example. Let's actualize what has been mentioned as rules. What if we have this? CH2, CH3, CH2, CH2, CH3, and then Cl. So, propyl, I think this is propyl. This one's ethyl. This one is chloro. So how do we number? So again, the most important rule that I wrote earlier. It's the reason why I wrote it. I could just say it, but just for emphasis, no. You want the number such that you are giving the lowest possible numbers around the ring. How do we apply that here? Let's say we start, we name 1 here, 2, 3, 4. What if we start here, 1, 2, 3, 4, 5? That wouldn't work, no? 5 is a bigger number compared to what we got earlier. This was 4 earlier. What if 1, 2, 3, 4? That's actually much better, no? As opposed to counting from here. Because you're giving 3 and 4 to the substituents. That's the tiebreaker. Earlier, rewriting it. As early as 1 and 2, we already got 2 substituents. So this is the counting that gives the lowest possible numbers around the ring. Okay? To give you a comparison, let's write a duplicate. So look at the difference. This one's not okay. This one's okay. Okay? And let's try to name this by alphabet, no? So by alphabet, chloro comes first, then ethyl, then propyl. So 4 chloro, 1 ethyl, 2 propyl, benzene. Okay. Next example. Okay, let's try to number. I'll play dumb. Let's just try this out. 1, 2, 3, 4. Okay. Could we get something better than that? 1, 2, 3, 4, 5, 6. That's much worse. How about here? 1, 2, 3, 4. Much better. That's the best combination we could get. Okay, so after numbering, let's start naming. So chloro and nitro. Chloro comes first by alphabet. 1, 4, don't forget di as a suffix. Dichloro, because we have 2 of them. And then 2, nitro, benzene. Again, 1, 4. Oh. Yeah, I did not. This is not nitro group. This is NH2, in other words, amino group. And instead of aminobenzene, we call that aniline. Sorry, give me a minute. Let's make a comparison. Actually, let me check something. I think there's something wrong with my answer key. I think we're doing it right, but the answer key isn't saying the same thing. So even though this looks better when it comes to trying to follow the first rule, the reason why this is what we choose is because this is aniline, right? So what matters more is that we call this 1 because it's not a substituent. We call the benzene ring and this one itself as aniline. That means these are the only substituents in the ring. So therefore, 2,5 dichloro aniline. So this is the name, not this. Or there's something I want to propose. Although I can't verify if it's correct, it's something that I'd leave as a question. No? 1,4 dichloro to yeah, I don't think that's correct. No. Rather, 2 amino benzene. Is this, are they the same? So that is my question. Okay, we'll leave that as a question for later or anytime soon. Okay, going back. So there is another rule. It's pretty rare, although you still have to follow it. What if you're given this kind of scenario? Cl, Cl, Cl. So you start, you want to start here, no? 1, 2, 3, 4. Let's try a different approach. What if we start from here? 1, 2, 3, 4. Ah, yeah, this is already something we encountered earlier. So this one is correct. This one is not. Because as early as in the first and second count, you already have a substituents attached to it. Here, yes, a substituent is attached to 1, but there's none in 2. That already is a tiebreaker. You have to take note of that. Okay, so now let's proceed to the scenario where we ought to name benzene not as a parent chain, but as a substituent. So there are two things you have to know. Phenyl group, abbreviated as PH, and benzyl group, for phenyl group, draw this, and anything could be attached to it. So the benzene itself is a phenyl group if it's directly attached to a parent chain. It is called a benzyl group if you see the substituent like this. So there is basically an additional CH2, no? That's the main difference between phenyl group and benzyl group. Simply just like that. Okay, C6H5. This one is C6H5C2. Sorry, C6H5CH2 and then dash. So the phenyl group is formed by the remaining 1 hydrogen from the benzene C6H6. Okay, benzene itself is C6H6. Let's have an example. A few, rather. Okay, let's try to name this. So, where do we start counting? Here? No. Here? Possible. Doesn't really matter whether you start here or here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Really, it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, desane, no? That is the parent chain. We have a 2-ethyl, 3-phenyl. Yeah, 3-phenyl desane. That's it. That is correct. Again, don't mistake. This is a phenyl group under the context that benzene is a substituent. You don't confuse it with this one. This is a phenol. Okay? You call the entire thing as a phenol. Okay. What if it were to be like this? Actually, it's very similar to this example. Let me just copy paste. Make some modifications. You might have guessed already. So there's just an additional line. So this is, again, substituents. We have 2-ethyl. 3. This is not a phenyl anymore. This is a benzyl. Benzyl, the same. Oh, sorry. This is not ethyl. This is methyl only. And following the alphabet, this one is correct. This one is not. What comes first is benzyl because B is mentioned earlier in the alphabet compared to M. No? Okay. So CH3 and NO2. This entire thing is a toluene. So we only have one substituent, nitrotoluene. We are missing something else. The substituents are ortho to each other, so ortho nitrotoluene. Next example. NH2. That's an aniline. Nitroaniline, para. They're para to each other. Cl, Cl. They are meta to each other. There isn't really a common root per se. Let's count from here. 1, 2, 3. 1, 3 dichlorobenzene. Yeah. Okay. How about this? Okay. So, do we start naming here? No. I mean counting? Nope. Here. We start here. 1, 2, 3, 4, 5, 6. This is a really important example. Why? There are 6 carbons in the aromatic ring. There are 6 carbons in the parent chain, the hydrocarbon chain. So what matters more? Do we consider this as a substituent, or do we consider the hydrocarbon as a substituent? Well, according to the answer key, we're going to assume that the benzene ring is still a substituent. So I guess, for example, we only have five carbons in the parent chain. That's when this chain becomes a substituent. And at the same time, this becomes the parent chain. Okay? So hexane, what? 1-methyl 2-phenyl MNOP. I think that's it. Sorry. This is not a substituent. Sorry, what's wrong with me? 2-phenylhexane. That's it. That's the name already. So there are instances where we need to consider RNS, the Can-Ingold Prilog system, whether it's cis or trans. If we are given a stereochemical assignment in the figure. But I'm not going to give out any examples on that. I hope there's none of that in the exam because there's none in our current syllabus right now where we actually solved examples on that for this exam. Okay, let's try to name this. 1, 2, 3, 4, 5, 6, 7. This is a heptane. This entire thing is a benzyl attached to the third carbon of the parent chain. 3-benzyl heptane. This one is a bromophenol. Bromo substituent, and then we have a phenol. As simple as that. How about this? They're ortho to each other, and they're the two of them now. Do we still have to number? 1, 2. According to the answer key, I don't think you have to, but just to make it look complete, I guess, write it. This one's interesting. So this is actually something famous. It's something that you see in Minecraft. If anyone plays Minecraft, whoever's watching. Let's try to crack it down first. This part is toluene. How many nitro groups do we have? 3. Let's number first. 1. No. Since we are gonna call this toluene, we start numbering from here. The substituent that is together with the benzene. Whether here or here doesn't really matter. Okay, so nitro appears in 2,4,6. 2,4,6 tri-nitro toluene. TNT. So the explosive, no? That's what TNT looks like. So as mentioned earlier, we have the Kekuli structure of benzene. It looks like this. It's the same thing as this. So alternating pi bonds. Benzene should have 3 short double bonds, alternating with 3 longer single bonds. I think that has something to do with the proposal, no? Regarding the Kekuli structure. We're gonna skip the parts where there's a mention on actual bond length of the benzene, 1.39 angstrom. It's very specific. I don't think that's gonna appear in the exam. The resonance hybrid of benzene. So if these are 2 resonance structures, the hybrid looks like this, no? Okay. Let's talk about the stability of benzene. We're gonna compare these three figures. Okay. So what are we doing in this process? Um, PD and C, this is familiar, no? Together with H2. What are we doing? We are reducing uh, our reactant. Yeah, we are performing reduction. More specifically, dehydrogenation. Yeah, dehydrogenation. So all of these end up just a cyclohexane, I guess. I think that's called a cyclohexane. Yeah, cyclohexene, 1,3 cyclohexadiene, and this one is a benzene. So the following compounds, cyclohexane, when they are treated with excess hydrogen, wait. Sorry. This is supposed to be hydrogenation. Reduction, one of its forms, one of the techniques performed is called hydrogenation. So there is a value, delta H. This is gonna be negative because heat is released. In other words, in context, it's exothermic. Essentially, we have what is observed and what is predicted. For the first compound, cyclohexene, it's the same. There is no difference. In 1,3 cyclohexadiene, there is a slight difference. So this is equal to negative 240. Essentially, the higher the difference between this and this, the more stable the starting alkene is. Here, what is observed is negative 28. What is predicted is just 3 times negative 120. So moral lesson, basically, bigger the difference, the higher the stability. Benzene is the most stable in comparison to the rest that's shown. Delta H is the heat of hydrogenation. So yeah, benzene is especially stable, even even more so than conjugated polyenes. So this unusual stability is very characteristic of aromatic compounds. So yeah, benzene is aromatic, no? it does have higher stability compared to other, at least several compounds. There are three categories. We'll talk about that in a while. For now, let me just read the notes. And yeah. An aromatic molecule with three double bonds is more stable than a normal molecule having three double bonds. So essentially, what we can get from that is that aromatic structure of a molecule can dictate its stability, no? And the reactivity of benzene is unusual in the sense that only certain kinds of reactions can be done to it or involving it. You blame it on the benzene's aromaticity. Okay, so it's very selective when it comes to what it can react with. Therefore, you expect reactions in alkenes not working with benzenes, no? So let's write this down. So let's say we want to add Br at 25 degrees Celsius and it's dark, there's no light. In some of the reactions, light is involved, no? Something you have to take note of. So there is no reaction, there is no addition of Br. What if we add KMNO4? Usually this is done when you want to oxidize. So involving water at 25 degrees Celsius, there is no reaction, no oxidation happening. What if we add ozone, H3O, and H2O in the presence of heat? So if you involve ozone, usually the attempt is to perform hydration, no? But there is still no reaction. What if we add H2 and nickel? So there is a slow addition. Assuming or under the condition that temperature is high, so is pressure. So the unusual behavior of benzene is not limited to hydrogenation. Instead, in the presence of a Lewis acid, the reaction is actually made possible. So earlier we tried to add Br2, no? We tried to perform bromination. But without a catalyst, several catalysts being a Lewis acid, you can't really perform the reaction. So one of the EAS reactions is halogenation, rather. Let's show it. So always the product will show that the benzene ring is retained. Basically, let me just show it by writing. This is one way. The catalyst being FeBr3. This is a Lewis acid. The outcome, we retain the benzene ring. For demonstration purposes, let's just show. Also, without even showing this, it's already understood, no, that there are, actually no, there is just a single hydrogen here. Carbon is, there are two bonds here, one bond there, another bond below. So 4. The carbon is not positive, not negative. It has no charge. let's just show the hydrogen here. So in halogenation, the first EAS reaction, it's either we add Br2 or Cl2, regardless of what halogen we add. Actually, no, FeBr3. If we add chlorine, this becomes FeCl3. Okay? In the place of hydrogen, we place bromine. And for the most part, that's what's most important to show. This is what comes together with it. Okay? In chlorination, another form of halogenation, so this is what you expect. No. Later, hopefully still within this video, we'll be able to go through the mechanism of each EAS reaction. It's pretty long, so I hope I don't die. This is a lot to cover. We're not even halfway yet. It's almost an hour. Not even a quarter of the entire coverage. Rather, not half. That's the wrong comparison. Okay, going back. Benzene, other characteristics. They are special, no? Again, they are more stable than the typical alkene, or the typical compound at least. They do not react with a lot of reagents. They have, they're very selective, no? So, in order to get past its selective trait, it needs a Lewis acid as a catalyst for them to react. Okay? When you hear catalyst, usually what comes in mind is that it speeds up reactions. Here, what you have to know for the most part is that it is responsible for at least making the reaction with benzene work. Okay? So, how do you know if something is aromatic? By the way, aromatic compounds are carcinogenic. Just by smelling them, you might get cancer. So, actually, even though it's kind of used in a jokingly way, if that's even a way of saying it, it actually shows how a certain set of criteria is important to determine if a compound is aromatic. So basically, you don't have to smell to determine if a compound is aromatic. There are 4 requirements. If a compound doesn't have at least one of these requirements, then it is not aromatic. Okay? So the first is that it is cyclic. So any cyclo, no? So it has to be cyclic. It has to be planar. Basically, if all the atoms lie in the same plane, in another way of saying it, it cannot be puckered. It cannot have a chair conformation. No? And the compound is completely conjugated, and it satisfies a certain rule, Haeckel's rule. So for Haeckel's rule, you have to know this, for n plus 2. It has to contain 4n plus 2 electrons. No? By the way, let's go back to this condition. I don't think I've explained this yet. So what does it mean for a compound to be completely conjugated? So it has to always be sp2 hybridized. In other words, the bond angle has to be 120 degrees. If the compound were to be sp3, expect there is no conjugation. Okay. Also, earlier, it's been mentioned that one of the characteristics of an aromatic compound like benzene is that the double bonds alternate. So yeah, that's very crucial. It's related to being sp2 hybridized. So let's say one of the double bonds is missing. This is already not completely conjugated. Okay, so if you're trying to determine, let me give you this pro tip. If ever the compound is identified to not be completely conjugated, there's a good chance that it is not planar as well. It doesn't apply to everything, at least usually. Okay, so I hope that narrows down your selection, makes your judgment better. So, what are the number of electrons that satisfies Huckel's rule? I am yet to understand completely what the n means, but for now, I found that it was survivable just by knowing these numbers. So 2, 6, 10, 14, 18, the interval is 4, no? If you know these numbers, then you'll be fine. How do you count the number of electrons, by the way? Let's have benzene as our basic example. You just count the ends of all of the pi bonds in the ring. So these lines, count their ends, 1, 2, 1, 2, 1, 2, overall 6. So this satisfies Huckel's rule. Okay, that's how we do it. What if we have this? Same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ah, okay. So this example, it does not fulfill Huckel's rule. Therefore, this is not aromatic. Okay. Let's try to finish. Yeah, we're almost done with the chapter on aromatic compounds. I think I want to take a break. What time is it? 11:58. Okay. I can't stay too late. Maybe I'll study until 3 a.m. I think 3 hours is a generous amount of time for the remaining syllabus. It's a good thing I'm doing this. It also helps me practice. Not only am I studying, I'm saying the rules out loud. So yeah, it does help somehow. I'll end the video here. In the next video, I'll be going through several practice questions utilizing this. No, you have to practice. It's not easy to it's not easy to not remember these. Okay, I mean, it's not difficult. It's just a few words. So yeah, see you.